have in the broadcast industry. Compare that to the IT, the information technology industry, where there's billions, tens of billions, maybe 100 billion pieces of equipment. So you just think of that in terms of economy of scale. If you're developing something for the IT industry and that many different things are being purchased, you can leverage off of that. The unit cost goes way down. And the other thing that the broadcast industry has been having, based on the fact that we talked about over the top in the last one, was you can now launch a live television service over the internet and get decent results. And in effect, some of the eyeballs that would normally go towards a cable company or a satellite, direct broadcast satellite or digital terrestrial television are going to a pure play of over the top from the internet. So in order to stay competitive, production and content delivery needs to really become much more agile, time to market based. And so broadcast industry specific interfaces and protocols and stuff are a bit of an impediment for that, which have a specialized header for that. So if we take a look at that, this is what a broadcast equipment center will look like in the 2020s. So starting next year on. Looks pretty much the same as your IT center, doesn't it? Now, obviously, I'm not showing some of the background cables on this, but this is the whole point. It'll be a rack of specialized servers, basically. Now, we'll talk a little bit about this because there's a term we use to refer to these generic servers that have broadcast industry specific software running on them now, but not necessarily hardware, except obviously for the intake card. And it's called COTS, C-O-T-S, or commercial off the shelf. So again, you leverage the software. This is the first step toward virtualization. Instead of having hardware-specific components internally, you do all those functions in software running on generic, again, COTS, commodity off-the-shelf servers. The only thing that would be specific would be the input or output interfaces because you have to talk to real devices, right? Otherwise, looks like an IT center. Now, that doesn't mean this doesn't have a higher quality of service. So you're not necessarily going to mix email on the same servers. You're going to be doing your revenue generating things, but at least you can see how you can have a common staff of people running it and managing it, things like that. So why IP for contribution then, and live production and play out and all the stuff that we normally do, right? And it really is all about flexibility and agility of the video plan. You want to be able to leverage basically commodity services and commodity switches. You probably have heard the terms network function virtualization or software-defined networking, SDN. And it's really about, in the networking world, they did it with switches, where switches used to be purpose-built hardware. Now switches in a lot of cases have high-speed switching end-to-end, the fabric itself, but the rest of it is it's all software. Everything's all software. One of the ways to move this, and the reason why I want to do this, is you want to have very much a flexible association of streams. Right now, in an SDI cable, no matter which of the 3 dozen standards you have, whether it's SD, SDI, or HD, or 3G, or 12G, or 3G, or one of the ones stereoscopic for 3D, that's a different one, right? Whether it's on coax or fiber and all this. Regardless of that, there's only one streaming service per it. So it's one video, can have multiple audio services on it, and associated data like the ancillary data field that we talked about earlier. But it's one. So one-to-one thing, which means for every video connection you have, if you're going to route it or switch it, it's an individual wire to do that. If you compare that to the IT industry instead, they can have the interface, regardless of the line rate, it could be anywhere from 100 megabits per second, to 1 gig to 10 gig. We have to do 25 gigs, 40 gig interfaces look like they're pretty much going away, be replaced by the 25, which will go right to 100. on that interface, they can have multiple services on them. In other words, multiple videos, and they have a flexible association. You know which one is where. How do you know where it's there? By its IP address or port number, right? You know what those IP address. If it's a multicast address, it's a unique multicast address, right? So you're able to flexibly associate the streams into the groups you want to have. You want to take advantage of that. So in the broadcast industry, we could have started over and invented something new, or we can look out there to see if there's anything that we can leverage off of, such as IT infrastructure, see if we can do that. Those types of information technology structures are inherently, therefore, more dense than what SDI ever could be, and it's also bidirectional. Very important. But the last part I want to emphasize is, if it's just a data stream being carried over, the actual payload doesn't matter. So you don't need 36 different SDI standards anymore. There's one carriage of real-time professional media over IP. So you need one. So if you think of the information highway as being the virtualized world, you know, you heard the term information highway, how everything is passed in that. This, in order to get on, you need an on-ramp to get on that. And this is the ability to do that for the video production plan. Now, I'm going to give a simple example of the basics for doing this, but I hope you don't, this is just the basics for doing it. It goes way beyond just changing from an industry-specific interface like SDI to a more generic IT interface, IP. That's just the start. But here's a nice practical example of this. So I swiped this from good friends of mine. This was actually done from the NAB last year at the IP showcase. Did anybody here go to NAB last year? Did you happen to make it over to the IP showcase? Or did you go to IDC, go to the IP showcase? So there's racks of equipment, of interoperable equipment on there. But one of the things that we're showing here was, this is an example of a 4K Ultra HD outside broadcast truck. So it's a big truck you roll up, put the dish up, you know, at an event, contribution truck. Basically, this truck here on the right has all the connections you need to do 32 4K cameras, 12 replay servers, and multi-viewing, you know, if you want the multi-viewers that you have in there, to do almost 500 unique sources. So it's a substantial truck, but that's not uncommon to have it in the truck. And what it is, it's 4 racks of equipment. Each of those racks is 37 rack units high. And you can see all the beautifully done 3G SDI cabling. Now, because it's a 4K truck, we talked about this earlier, it's 4 3G SDIs per 4K, and it's a quad standard for that. Now, it is true that it's now much more common to see a 12G SDI right now, but that's relatively new and is more expensive, so they wind up with that. If I take the same function, so the same bandwidth and the same function, but I implement it using IP switches instead. So we're going to replace SDI with IP. We haven't said how we're going to make that work yet. I'm going to say if we were going to do that, okay, then it's 1 rack unit, 10 rack units high. Now, this is an outside broadcast truck. So think of the substantial difference here. Not only does this fit easier in the truck, so you can either use a smaller truck or you can put more stuff in it, right? But remember how a truck operates. If I have all that equipment, it generates what? Heat. It also uses a lot of power. I need to have a generator on there or run it off of petrol, one or the other, right? You have to do something. And I got to remove that heat by doing what? Air conditioning. And I have the weight of all that equipment and the weight of all the air conditioning and everything else. So imagine that and the difference between them. This is a substantial savings. Just by going to all IP, with nothing to do with any of the other advantages you get by going with it. So this really pretty much tells you quite a bit of why you want to drive towards that. So starting around 2013, which in years doesn't seem that long ago by naming it, but it's 6 years ago now. It's quite a long time in the world of technology, right? We decided we need to start talking about doing this. How are we going to do IP standards? Where are we going to go? What do we do with that? Because there's more than one way to do this. I love this. This is a real street sign in New York City. Obviously, something's a little astray here, but we really need to get together and do this. And you can come up with one vendor or proprietary solutions where you can try to solve it for the whole industry. This is the purpose of standardization. We're not doing HDR here, right? 6 different ways. We're going to do one way. So by doing that, we end up with consensus on doing something one way. We don't want to end up like this picture here. This would be bad. This would be really bad. We need to line up or we lose all the network effect and the economies of scale doing all IP. And we also want to do this as an underlying foundation with which to build higher level applications, because once you go all IP, again, it's not necessarily, I gave a great example with the truck of why just doing that is advantageous. But by going all IP, you can leverage off of all the apps that are already written out there for IP, and you can use them for broadcasting. So it's a big gain for doing that. So in 2013, a group of 4 industry associations, the Advanced Media Workflow Association, AMWA, the European Broadcasting Union, the EBU, the Society of Motion Pictures and Television Engineers, SMPTE, and the Video Services Forum, VSF, got together and formed a group informally with a mission. It was called Joint Task Force on Network Media, or JTNM. And you can actually look them up. It's on the web for this. And the whole point behind this is, how do we move together to go off of industry-specific interfaces to something more generic? We know that going to IP is probably the way to go, because if you go back to when SDI was invented 30 years ago, how did we use it? We had a pad of paper, you connected 2 things together, you wrote the port numbers down, you stuck it on the wall, because nobody had these things. They didn't exist, right? So maybe you take the pad of paper and you run over to a mini computer, type it in to a chart, and then you'd print the chart, and then you took that and you stuck it on the wall. It's basically the same thing. And when you made a connection change, you took a pen, you did that. It's not really the best thing on the planet, but to do that, but it worked, right? But since then, 30 years later, we now have multiple devices. I'm sitting here with 3 internet-connected devices right here. Okay? I know most of you have more than one. Maybe you're not crazy enough to have 3, but many of you will have 2, right? So we knew there was something with this and leveraging that. And again, instead of having tens of millions of broadcast-specific equipment, we're going to have hundreds of billions of IT-based equipment. But IT stuff doesn't do real-time video. So we have to take a good look at how do we make that and leverage it up. And that was the point behind the Joint Task Force. So let's look at what would an all-IP architecture look like? Where are we now? Where do we need to be? And we do like you do with any other project. You do a gap analysis. What are we missing? And then you lay out a roadmap. How do we get from where we are to where we need to be to close that gap? So it's all about fostering the broadcast transformation with the end goal of moving from media-specific to IT-based interfaces, protocols, and infrastructure, and under the guise of this project being known as real-time professional media over IP. We can see video over IP for years. We just talked about adaptive bitrate streaming. That's video over IP. That's a consumer application. We want professional application that needs to support real time. So that's the big key for this. So we got together and actually published this architecture document, and then laid out, here we go, and then laid out a roadmap. I know you can't see that from the back of the room. Again, I'll give you this, but this is a map. It started back in 2014, going forward. This is the last one that was published last September. Now, when you do flow charts for work, or timelines or roadmaps, right? You do them by quarter or you do them by month. But you got to put this in context. This is the broadcast industry geekdom all getting together to do this, right? The geeks all getting together. I'm one of those guys. So what do we do timelines in terms of? Well, of course, NAB and IBC. So that's the timeline on here. It starts at NAB 14, actually it starts at IBC 14, goes to NAB 15, IBC 15, NAB 16, get it as you're going forward. We start at the lower left here where it's current SDI, and we show how do we build up that gap to get to the end goal, which is at the top right, which we have coined a term called the dematerialized facility. Big term, dematerialized facility. What does that really mean? It means if you're truly in a cloud and virtualized world, you don't know where your broadcast facility is anymore. It could be anywhere. Heck, I'm gonna like that because I'm a broadcast engineer. I don't feel like going to work one day, assuming you've solved the problem of security, big one, especially with IP networks, but assuming you've solved the security one, and you can do more than just a VPN, but a really hard interface. Stay home, pee in your PJs, drink a cup of coffee, and do the live events for the day. It could be all over the country. It could be all over the world. And it could be multiple one virtualized facility, but multiple physical locations. That's the end goal. And we're nowhere near that when we started in 2013, 2014. And we're not there now either, but we're rolling up this stack to these different things. It starts with SDI over IP was the first thing, for those familiar with SMPTE 2022. Then it was about breaking things into elementary flows and then doing network and resource management. We're just rolling up on that. So let's talk about that a little bit. So these are the stack of standards to close the gap. What do we need to do? So we start at the very basis on the bottom. It's known as media flow transport. That's actually putting real-time media in IP, right? Just getting it in there. You got to package it up and get it in there. Not that hard. We've done it before, but we need to do it in a way that will allow us to be able to leverage off of IP infrastructure better. Again, the goal is not just transport it over IP. It's to fundamentally use the IP technology. Next step. Well, in SDI, everything's on a single cable. So everything's lined up timing-wise to the video frame, right? All the SMPTE 12 timing and the clocks, blackburst, everything else is all lined up, and it's all together in that. You still might have lip sync problems, but that's a different issue. But you know that your audio and your videos are all together. You know where to find them and how to do them. That's the good news. The bad news is when you want to work on them, what do you need to do? A specialized industry-specific extractor or de-embedder. Then you work on them separately using the house clock, and then what do? You do an industry-specific embedder, or re-embedder. And it's over SDI again, right? All over the place. You do this all the place. Big giant SDI switches. We have these embedders and extractors everywhere. When you're in the IP network, what are you doing? It's just a logical flow. Think of it, simplest terms, it's a multicast stream. So now you got over a single cable, a multicast for video and a multicast for audio. They're no longer, they're on the same physical thing, but they're on the same physical thing with hundreds or thousands of other streams. So you need to really do really great synchronization between these flows, or nothing's going to work right. You're going to have never mind lip sync problems. You're going to have, nothing's going to work right. So we have to work on that. Next thing is, because we have multiple things in the same physical thing, we need flow descriptions. What is it that I'm carrying here? I need to be able to tag something and know what it is. Before it was easy. It's a frame that came out, it's SDI. You know at this timing point when you see end of active video, you know where the bank is. You don't want to line things up. You see the include signals, everything else that is in there, and you're able to reline things up for the start of active video next time around, and you go. You don't have any of that. It's data bits on a wire that's in an IP frame. So again, describe. If I look at this IP multicast, what is this IP multicast? We need a flow description for that and have it be meaningful. Here's a good one too. You want to be able to find what you have automatically. You don't want that list on the wall anymore. What's important for? Oh yeah, hey, that's this cable over here. and then you find out it's not because your coworker switched it for an event last week, was in a rush because it was a live event, didn't want to miss the timing window, didn't take a note down, completely forgot about it, and the wire is not where it's supposed to be. What you want to be able to have is a discovery of something when you plug it in, have it be registered and ready to be identified by anything else on the network. What's that sound like? Sounds a lot like one of these guys, right? We take it for granted. Think about this little miraculous thing that we have here that we love so much. The ultimate sneaker network, bringing stuff between people without using the wire. I take this as a USB port. I randomly plug it into anybody's PC, whether it's even different operating systems, Linux, iOS, Windows. You plug it in, boom, it gets discovered, it gets registered. Device figures out, I need a driver for that. Is it local? Is it not? Goes to the internet, gets the driver for it. Next thing you know, it's been identified as an available device on your system, and you can access the files on it. Never mind the fact that the file system is different between all three of those major OS that they have, but they're all able to read this thing, and then you pull it out. Of course, when you're doing it, you just plug it in, share the file, put it in the folder, and you pull the thing out. You don't even realize how much is happening to do what is called universal plug and play. Why don't we have a universal plug and play for video equipment? No, same as this, but wouldn't it be great if you take the back of a camera with an IP connection and you plug it into a multi-viewer just so you can see what's going on, or through a switch, and it all just recognizes stuff starts working without you having to do anything? Great concept, right? Well, that's what we're talking about doing. All right, now, if I just have mayhem, you know how the internet works. Everybody wants all the bandwidth all the time. So what do you have a lot? It's a collision of stuff. You get delays. Packets get lost. Yeah, not going to work so much for real-time video. You're showing an event that's live and you're losing packets. You can't get those back, right? So you need to be able to do flow control into the network and out of the network to make sure that you have a quality of service or service level agreement, SLA, or quality of experience you'd expect from a broadcast interface. So you can do those. So the first step towards this is a brand new suite of standards. It's less than a year old. It's called SMPTE ST2110. And this addresses the bottom layer on that. And basically, all these different parts of the standard, from a systems layer, uncompressed video, the timing of that video, uncompressed audio, transparent audio transport, the new one for compressed video formats like lightly compressed. And then what if we talked about between multiple services in one pipe, because if you have 100 gigabit per second Ethernet, you can put, a handful of 4K signals in there. Well, what if it's the other way around? What if you don't have that? You only have 10 megabit per second Ethernet, but you have a slew of them. You want to segment it up, sort of like the 3G SDI doing 4 to the new 12G SDI. So we have a single video asset transport or multiple streams. So we do it that way as well. The good news is all of these parts are approved and published already. It's done. Interrupt testing has been done. The last two pieces here are close to being done. They're not published yet. That's for compressed video. And it's a generic compressed video standard. Although I think the first one that's in there, I believe, is TCO. And one of the JPEGs, I think is the first one. But it's a generic carriage in compressed video. There's enough information in there so you can tell, again, what type of compressed video is being carried. Because even though it's all about production, which you want uncompressed, there are cases where lightly compressed would be good to have as well. So this demonstrates the power of IP right here. Remember those 36 SDI standards we're talking about? It's because we started, this is the protocol stuff. We started at the fiber or copper level. We then had a data link level. We then had a networking layer. We then had all the transport protocols. And then we have the essence on top of it. For every single different everybody get that? for every single different uh, fiber or function was always starting from the beginning and all starting over industry specific. Meanwhile, there's Ethernet out there. There's IP. There's UDP and TCP. There's RTP, real-time transport protocol, RTP. So why not leverage off of that? And that's exactly what 2110 does. So we have IEEE standards at the bottom, which is the physical fiber and copper, and then the data link above it, which is 802.3 Ethernet. And then we have, everybody knows who the IEEE is, right? Everybody? Institute for Electrical and Electronics Engineers. We then have the IETF, the Internet Engineering Task Force, where we define the Internet protocol itself, the user datagram protocol, and the real-time transport protocol on top of that. So now we have a way of doing real-time video on top of it. So what do we need to define in SMPTE? Society of Motion Pictures and Television. People that brought you SDI are the people that brought you 2110. Now we have video, audio, and ancillary data as a application function on top of that transport. So good news in multiple ways. One, we're not reinventing the wheel. All the lower stuff works. We might have to pay attention to timing on that, make sure it meets the quality of service we need for broadcast video, but we don't have to reinvent the wheel as long as the underlying can handle that. And we know that banking and commodities trading happens on the internet every day, so we know it works. It's just a matter of keeping timing tight. Right? So now we have one set of standards regardless of the video format. All the same, just encapsulation. This is a key differentiator. So the elementary flows over IP. Now, you have things called devices and sources and grains and flow IDs and flows and all this stuff being tied together. All of those terms, with the autonomous unit being a grain, is all defined in that JTNM roadmap and architecture document that I described to you earlier. Joint Task Force for Network Media. And they all tie it together. And there's a time base that has to go to connection groups. You're going to put all these, a baseline grain could be a frame, right? A video frame could be a grain. And then a sequence of those frames, there's a flow, like you have like a service that's coming out. You take those flows, you group multiple videos and audios and maybe ancillary data together, that becomes a connection group, and then you make the connection. A source is where it comes from, a sink is where it goes to, different types. You're seeing how this is all tying up as an architecture. So we did for a number of years within SMPTE have, of course, video over IP, professional video over IP, but it was SDI as a whole inside IP. So that's on the left. So if you take a look at this, this is SMPTE standard 2022-6, which is affectionately known as SDI over IP, although that's not what it's called, as we all know that. In the IP layers, but the SDI layer itself, the SDI framing is the next layer that's dropped in. And the audio, the video, and the embedded data are all as SDI. So it's transported over IP. But when you get to the endpoint, what are you doing? You're unpacking it, and what do you have? SDI. Which means you still need your embedders and your extractors, et cetera, things like that. It's still SMPTE 12 timing, everything, nothing, it's not using any IP service. It's just using the network from point A to point B to get it there. Similar things though, it uses RTP and everything like that. What 2110 does is it's essence-based encapsulation. So you can see the difference here. If you look on the right, there is no SDI layer. It doesn't exist here. We have the video, the audio, the data, and the timing all dropped into IP and synchronized. Very important distinction. IP native. All the benefits of IP. All the problems of IP. Okay? And there are lots. But the point was to really, truly leverage it off. Think of it this way. This is not the same thing as going from analog to digital. Think of this as the difference between going from the days when all of our content was on tape and you had massive tape libraries. In order to get access to a program on a tape, you had to put it into a linear playback machine, go to that portion of the tape and either physically splice it or have another tape next to it and get the piece off. And that's how you did all your programming, your news feeds, and you do the news show and everything off of that. And then that could, instead of running around with that sneaker net was, they really do mean sneaker net was tape, you can put it in a robotic system, but what did the robotic system do? It grabbed the tape and put, it's the same thing. Then we converted tapes to what? Files, and the whole world changed. Now you can sit at your desk, and anybody else, you can access files. You can edit them any point instantaneously. So you don't think of a file as being a virtual tape and just use the function that way. Once it got converted to a file, you leveraged off of all the access things you could do with a random access file. That's what converting to IP is all about. So leverage all the power of the internet protocols, all this stuff that's out there, not just carrying it and transferring it over IP. Very important distinction there. So think of this as the same great thing that went when you went from content going from tapes to files. This is the delivery of said content. So it uses RTP as its basic lineup in that. It's separately forwarded elementary streams. We have to worry about video flows, audio flows, with the ancillary data. We have clock distribution, which I'll talk about in the next slide, and synchronization of those. If you notice, every single step along the way here, it's either been developed as a joint specification or leveraging off of an existing IETF in the engineering task force, because they're the internet experts. They don't know broadcasting, we're the broadcasting experts. They know that. So a lot of this stuff is leveraged off of that. Maybe the spec was mostly there, but needed to have a new version or something that would make it a profile that works for broadcasting, which is exactly what we did. So as part of that task force, we went out to say, how are we going to replace Blackburst as our venerable timing for the entire thing? I mean, that's how SDI works. That's how your station timing works. You use SMPTE 12 timestamps. It's all based on old analog concept of Blackburst or Blackenburst. So let's go out and take a look at that. Why again? Same thing. Why are we reinventing the wheel? Is there anything out there that already exists? And after a lot of research, we figured out that there is something. IEEE invented it. 1588. What was it originally used for? It's to do secured, reliable timing information for the commodities industry. You're buying and selling stocks, you know, out of order stuff, big difference. Which one arrives first, what you pay for a share of stock, and heaven forbid it get lost or dropped, just like real-time video, or it gets jittered, right? You have to cover that. So we looked at that, and it was already being used by the finance and commodity industry. However, they have no idea what a video frame is, right? So we had to do something to tailor the precision time protocol, PTP, for broadcasting. There's a SMPTE suite of standards for that as well. It's SMPTE standard 2059. -1 is basically a definition of what's known in PTP as an epoch, which is a time from which all other time is done. We use the same one that they did. I forget what year it is. It's like 20 years in the past. And then all the alignment of all the signals that are on that. And then we have another part which talks about a profile for how you use PTP for professional broadcast applications. Things like video frames are defined and how you align them. And then, of course, we have an engineering guide that tells you all about how the new system works. So 2110 is the transporter of professional media inside it, and it won't be worth anything if you can't synchronize it, so it has to work hand in hand with 2059. Now, if we're going to do this, though, PTP isn't really a internet protocol. It's IEEE. And what's the internet timing protocol? That's RTP. RTP isn't precise enough, so we have to play some games to match up RTP and PTP together. As it turns out, the broadcast version of RTP, we use another 8 bits for additional timing on there. But the way it works is you have a master clock, you have slave clocks, and you actually have these things called boundary clocks, so you can tie it down to a region for that. And you can actually have multiple master clocks that talk to each other to find out who has better clock accuracy. Eventually, a PTP clock master clock will go towards either GPS or one of the cesium clocks around the world. It is that precise of timing you have to do it. And you relate it back to RTP through RFC, that's an IETF document, RFC 7273. And there's something called the session description protocol, which I'll talk about next slide, that ties the timing of the clocks together. So you have it for that. So speaking of session description protocol, this already exists out there. A session, of course, has state, and STP is RC 4566. We had to modify it or come up with a version that would work for real-time video, and then we do that through an RFC, which is another RFC 4175, which is RTP payload format for uncompressed video. And we added things like colorimetry, dynamic range, things like that. But the cool thing is they already had a failover strategy. What happens if you lose the packets and stuff? So that already worked with that, and so we use the same structure for that, which is duplication grouping, which is another RFC. So winding down, we have IEEE, SMPTE standards, IETF, RFC. By the way, anybody here know what RFC stands for? Request for comment. It has got to be the weirdest name to put on a standard in the Internet standard. RFC, request for comment. Because that's how it started. It was put out on the internet. We're requesting comments on this, and they standardized it based on very old, and they have to all be in ASCII text. No formatting documents. Everything's done. All the specs are in ASCII. Very strange. Just simple text. Okay. Now we just spent all this time talking about putting that lower layer. Remember this layers of specs? Putting that lower layer on the network, then identifying the flows and timing them all together, making sure it's all locked in. But we haven't talked about how to manage them yet. Remember, that's just video or media over IP. We need to be able to manage them and interact with them. So if you're going to transform this is where it really goes to the disk to file analogy is right here. You don't want to do static configurations. You want dynamic configurations, and you want a way to do it that's not cumbersome. And sure, would love to do it automatically, right? All the benefits of IP, all the banes of IP. So you have problems such as determinism, security, all that stuff needs to be addressed. But this sounds like we need a smarter media processing system, which is very similar to needing a smarter networking system. So is this the same type of concepts of SDN, software-defined networking, or network function virtualization? Isn't this software-defined media processing or media processing-defined virtualization? Let's do the same for media processing. We're going to separate out the control plane, defining the connections, from the data plane, the actual traffic carriage on that. And then use standard interface or APIs to associate between the layers. This is where AMWA comes in. We have something known as Network Media Open Specifications. It's not quite open source, but it is available on GitHub. They're not standards or specifications. AMWA is not a standards body. I would love to see them take these to SMPTE to get standardized. Hopefully they will. But it solves two major shortcomings that we have with the industry-specific SDI that we have right now. We've talked about both of these, but just to remind you, discovery and registration. I really want to find out what's on my endpoint, and I don't want to do it manually. You already know this. If you plug an IP cable into a wall in a network, you get discovered. Your device gets discovered. Do it every day. You go to a hotel, you plug in, or you do Wi-Fi, or you plug in. You're getting registered with the network. Same thing. Let's get in there. So you want to find out about the endpoints, what flows are available from that. In other words, what are its functions? Put them in a shared registry and provide a uniform way of querying that registry so you can use it. And then once you have all that in the registry, then you can do connection management. You can actually form a connection between these devices that you've discovered on there. And identify them as association, and they have state. They become a session. And these documents were developed through an incubator, the NMI they called it, the Network Media Incubator events, basically. So it's, I want to be clear about this. It's not UPnP like the little hand device I had, but it's analogous to that. No manual entry of IP addresses and port numbers. And the first three documents that came out were IS 04, 05, and 06, discovery and registration, connection management, and network control. All of this stuff follows the JTMN reference architecture. So real quick, because there's not a lot of time to go over it, this is that whole plug and play thing. In the registration service, you plug it in. It does sort of like everybody here familiar with DNS? You understand DNS, same type of concept. It looks for assignment. It gets gets initialized, it gets to be a type of device, it gets put into a table, and then you have a query service that can query what you are. So basically, that's how you associate basically, your email address or your server address are name with a name. It's a dynamic name service. Attached to it. The cool thing about this service, though, for media, as opposed to the internet, the standard internet one, is you can do peer-to-peer recognition. That was what I described earlier. You can actually plug an internet-enabled camera. In other words, the output of the camera is not SDI, it is, or HDMI. It is IP. You plug it into a multi-viewer that's IP that follows this. They'll discover each other, and whatever you're recording the camera will show in the multi-viewer. Normally, in a regular network, you need to have a switch or some type of a manager to recognize. This does it without. That's kind of cool. Connection management now is, again, remember we talked about the JTMN model. You have the stream, which is carrying it. You have connections. You have the sender, receiver, flows. All these things interact. It's managing all your connections. I mean, and the state of that. So that's connection management. That this is very similar to doing the network function virtualization stuff. And everything gets registered as an active streams or active connection until it gets later. You can tear it down and then reuse those resources get released. And this way, you know what resource tied up in the bandwidth is required for that. This is basically software-defined networking here. It's just been renamed. You now have a broadcast controller on top of a network controller. And what's a broadcast controller? It looks a lot like what you have today for a traffic management system, right? But it's going to talk to a generic network controller now. And how do you connect to a multicast? IGNP, Internet Group Management Protocol. Or you could use the new M106 one that's available. What I'm saying is there's all these different ways to do it. It's IP, it's all IP based, leveraging all the IP work. So based on this, the stack of standards is stacked up. So this is how it all gets implemented. So we've done this fundamentally. Things that are being addressed now that I don't have in the slide deck, they're starting to get involved with security now and encryption. Because clearly, if you're going to dematerialize a facility, you have to make sure that only the people that are authorized get access to the flows. You don't want someone stealing your content, right? Or even getting, or worse, taking over your studio remotely, right? So, like I said, all the power of the internet, all the problems of the internet. So you get both ways on this. So is this real or not real? Well, we've been doing these interops now for about 1.5 years. The last big one at IBC was over 50 vendors show internet. These photos actually, I got lazy and didn't get the photos off my camera. These are from actually NAB of last year, but it's the same concept. They have all these little demos and racks of equipment. They actually did a live, both at IBC and NAB, did a 2110 based live production on the floor. So, if you go to NAB or IBC, they both have live television production that they've always done over the professional studio. This time they ran it all on 2110. It's pretty impressive. At NAB this year, there will be an IP showcase, but we've gone beyond the interoperability point this time, so we're not showing the big interoperability. Companies such as MediaKind, we're going to show the equipment in our own booth. The testing is actually going on this week, the pre-stage for that. I'm pleased to be told that our RX1 receiver that is fully implemented the 2110 stacks was passed the test yesterday, and they have this thing called JTMN tested gold seal of approval, so we'll show on. That's how they're doing it this year. And it'll be in a book of available documents. If you get a chance to stop by the IP showcase, if you go into NAB, there is an IP showcase theater with a lot of stuff. As a matter of fact, on Monday at 2 p.m., I'm running a panel talking about, what are the pitfalls, how well have you done all IP-based productions with some of the largest 2110 implementations in the world. The users are actually going to be on my panel. So that should be pretty good for that. Any questions on this before I move to the last topic of today? Everybody's an expert at 2110 now. The difference between 2022-6 and 2110. all IP versus SDI over IP. Fantastic stuff, right? Yeah, okay, I'm not getting warm and fuzzy here. Interesting topic?
Yes.
Yeah.
I have a question.
Yeah.
Because we have a big discussion between 2026 and 2110. Between distribution and production environment. What is your guess on when you have to choose?
Yeah, so if you're already using 2022-6 and you don't need to extract an individual signal, or you're just sending it back and forth through, there's no point in going with 2110 just to use it. Just transport the 2022-6 between endpoints. The advantage using 2110 is you get rid of all the embedders, de-embedders, and the custom equipment. If you're not doing that, don't do it. And I'll go a step further. If you're a small production house and you're not ready to go IP, SDI is not going anywhere. Stay with SDI. Analogous for that would be, some people aren't even broadcasting in HD now, they're still doing SD, right? Even though 4K is being talked about, if it makes commercial sense for you, you go to it. If you're gonna build a new studio now, I absolutely would go 2110. If you're building a new studio. If you have existing ones, you're not, you gotta weigh off how you're gonna do that. So and that also means that the interim, that there'll be a lot of 2022-6 SD over IP stuff still out there. There'll be islands of SDI, islands of SDI over IP, and islands of all IP 2110. Just the fact of life, what we're doing. If it makes commercial sense, you use it. If it doesn't, it doesn't. I will tell you that the wave of the future, though, for the most flexibility, for the reasons I gave, particularly if you're building larger stuff, it's going to be 2110. And if you're doing 4K, think about it. Why would you build a new 12G plant from the start? Why not build a 2110? And you'll handle UHD, you'll handle HDR, you'll handle all that. There's going to be gateway functions everywhere for a long time. You know what I mean by a gateway function. You give it a 2110 signal in, and the output, or vice versa, is going to be SDI over IP or just SDI. Analog, I suppose. So we really are talking about monitors having a 2110 input on it. It's going to have like an Ethernet connection that knows 2110. So instead of, in addition to SDI, I can't imagine monitors getting rid of SDI anytime soon. I'm talking about professional monitors. This is the consumer one at this point. HDMI, of course, goes to the consumer. Any other questions on this one? All right. Still with me? Oh, one other question, yeah.
Yes, about the network design. Which vendors are ready for?
Oh, God. There's 50 vendors, 50. I don't have the whole list in my head, but pretty much every major player out there. So if you name one, like I don't know who you're using right now. Pick it up. Tell you.
Cisco.
Yeah. Cisco's doing 2110 switches. I don't know what the state of them are. And so is Juniper, so is Arista. I know I've missed here a couple, but for switch wise and around there. Vendors, we're migrating our whole line of equipment over to it. Not everything we have is 2110 today, but you just heard that we have one device. And oh yeah, no, we were part of the big interrupt. Yeah, the interrupt this time isn't. We're not showing devices interrupting in the IP showcase now, but to pass the test, you had to interrupt with, I forget how many pieces of equipment, so the setup equipment. And I already have my engineer that's on site. If I wasn't giving you the seminar, I would be there right now. But he's on site and gave me the good news last night that we passed with flying colors. It's not easy to pass these tests. I mean, particularly in our case, it was even more so difficult because I didn't explain this earlier because it just didn't get deep enough. Because it's all about cloud-based things and virtualization, our implementation that passed is all software, including the traffic shaping function. A lot of the switches will do what's called a wide sender or a wide receiver, type W. There's also type N or narrow, which uses hardware-based interfaces. But we wanted to see if we can make this work using COTS, commodity off-the-shelf server. So we're very, very happy. And the person who, the engineer who's running the JTMM experiments is actually from the EBU in Switzerland, Geneva. His name is Willem. He's over the moon. He didn't think, because the EBU wants to use all COT servers. He didn't think anybody could build this. He thought it was years out. So he was very happy when we passed the test today. So that's great stuff. Anything else? You guys all ready for another long topic? Ready? I'm sitting between you and your break. Lunch, whatever. Okay, so we talked about the interfaces and everything, and we alluded to software-defined media processing, but I didn't really say what software-defined media processing is. But I hope you understand as an interface or connections between things, it's very clear around why there's motivation to go all IP, right? I hope you guys all got that from the last time. This is going to take it a step forward. I'm going to give you the motivation of why you want to go to all software. Now, that said, there are a few companies like MediaKind. We still do all of our media processing equipment in purpose-built hardware because we have customers that still want that. But if you're going to have that broadcast center I showed you in the 2020s, you need to move to either COTS or something that's COTS friendly in order to do that. So let's talk about this. So not too many years ago, everything with media processing. When I mean media processing is a generic term. We're talking encoders, professional receivers, IRDs, integrated receiver decoders. Ronaldo, could you do me a favor? Can I get some more water, please? Sorry. That'd be awesome. Thank you, sir. Handle it. So everything was done with purpose-built hardware for the same reason it was done with the SDI. There's no way you could get real-time, high bit rate, high quality video through it. So encoders, receivers, multiplexers, translators, format converters, transcoders. Did I miss anything? I think that's pretty much anything that's media processing. Right there. Thank you, sir. And the reason why everybody wanted the best bit rate at the lowest latency. That's the chart. This is an older chart. It shows first generation, MPEG-2 versus MPEG-4, where the bit rates were over time. And you needed purpose-built hardware to achieve that. There was no, you could do a little bit for decoding, but for compression, there's no way you can run that over a CPU. It just didn't have enough power back in the old days. And if you've ever seen one of these spider graphs here, it was always a trade-off between picture quality, its compatibility with IT equipment or the cloud, how agile your development could be on it, reliability. You make everything off of a server, you have the reliability of a server then, whereas purpose-built hardware can have 6 nines for reliability, right? And power efficiency. You got a big hungry server versus something, a piece of equipment that's dedicated for it. Usually less footprint, smaller, lower power, faster, everything you get from that. So flexibility was always traded off. It wasn't flexible at all. It was an encoder. It did one channel. It did it well. That's it. There's none of this fancy stuff. Now it's the opposite. How do I make it go into the environment? And I'm showing you the spider curve. There is different types of implementations here. If you want the best video quality, the best reliability, the best power efficiency, that's the orange one. That is a purpose-built hardware-based encoder. And the other ones here are showing other combinations of those. And because everybody really needed bandwidth as such a limited commodity, you never had enough bandwidth to do all the channels you want to do. This was what was really important. Well, times they be a changing, so they say. So the market challenge now is keeping in mind you have to have a high quality of experience. If it's not a good experience, you're going to fail. You can't take forever to come into the market. You need rapid time to market, and you need total cost of ownership optimization. You can't have it be economically unviable to do this. So in the background of all this is the same type of driving forces that we talked about for the move to all IP on the interfaces. We got all this virtualization and software processing on COTS servers, all the way off the shelf COTS. Talking about the cloud, everybody, the cloud. You know the definition of cloud, right? Just means it's somebody else's computer. Right? people talk about the cloud. It's still running on something. It's just not, it's virtual. It's not yours. It's not a physical appliance that you have. You're leveraging it with other people. The cloud conveying and how things get moved in them is really showing a much more viable leasing model or per service as a service model versus owning your own infrastructure. It's getting more and more. And people want to leverage off of that IT stuff. I already told you the IT stuff. People want to leverage off of that. And we're getting multiple cycles of Moore's Law and new processing power and CPUs that's generic on the market while we're trying to build custom hardware. The custom hardware obviously takes advantage more, but it's a longer and expensive process for doing that. And again, the IP transformation is not just about carrying things over IP, it's about using the tools. You already have those tools for your IT department, for your other functions. Let's leverage off of that. So again, though, you have to have the QoS and stuff like that. So we're going to call this the internet era of TV chaplainship, right? You need to launch new services quickly. Do that, right? You need to maximize revenue from content. You got to maximize that, otherwise you can't afford to do it. So you try to recognize ways you can monetize. I mean, a classic example of that, one of my favorites, is taking old cartoons and building a network based on old cartoons. Who would have thought that would have worked, right? The Cartoon Network makes a lot of money. Everybody loves cartoons, okay? But you know what I'm saying, these specialty channels that you wouldn't have thought about before. You want to simplify operational processes, and then you want to leverage off the latest technology. We talk about HDR, 4K, HEVC. And to do all this, you need to have operational efficiency. You want to have choices or options for your deployment methods so you can maximize content. You want the most bandwidth efficiency you can. Again, that's what we call Q over BW, which is the best picture quality for the bandwidth. And you got to do this rapidly. DevOps or agile operation for that. If you don't do this, you won't be able to compete. So how do we get there? This is where we started. Everything was appliances until a couple of years ago. Everything was an appliance. When I be my appliance as a fixed piece of purpose-built hardware that you would have connected. Maybe it had a software interface on it, but it was that software interface was for that appliance only. It didn't talk anything over that. And what we want to move towards is we still have to have physical appliances. I mean, it's a camera. What's the camera? Remember? Transfer function, optoelectronic transfer, right? You had to have, it's a physical device, a display, same thing, a microphone, a transducer, another type of transfer function. But you want to take everything else you have, right, and make it into an application. So all the other stuff that you're doing is an application that's running on that. And then you can ride all that on top of either commodity off-the-shelf service that you have, custom hardware, or somebody else's server, which is the cloud. Okay? But if you do it this way, all this runs, the same code runs in all three. This is the beauty of this. You don't have to write separate code, separate things for it. So there's still a need for some custom hardware, which I'll talk about later. But the point is, you're reorganizing how you're doing. You're basically, you're doing software-defined media processing. You're abstracting the function from the underlying hardware it's running on. Okay, you're abstracting. That's the key. Think that abstract. So the value of virtualization in the cloud network, we're talking about this, is really about the bottom line. CapEx and OpEx savings opportunities by doing hardware cost reduction. It's infrastructure agnostic, which means you can leverage it with multiple tasks. You get full automation and task time to market, and you can grow revenue growth by having new experiences, customer experience stuff, streamlining things. You leverage network infrastructure, you streamline the services, enable cloud, and then you basically develop your business accordingly. You could save 50% of what you're paying now by doing this stuff, just this. That's the value of virtualization moving towards the cloud. So in this point, well, that didn't go. There we go. So you want to be able to boost your operation, improve your efficiency, agile, do a fast rollout. So I'm going a little bit faster than losing people. As a service, you can offer things completely in a leasing model now with tokens. Okay, you can do live on-demand events as a service, and basically you don't even own the device inside. You're running it. Or you can even get new applications. You can do scaling through offloading and rebalancing what you have. Maybe you have a disaster recovery technique where your disaster DR location, disaster recovery location is located somewhere else. You have your own servers on site, they're yours, but your recovery is owned by somebody else. They could leverage the cost for that. And of course, you can do targeted ad insertion of that. You can do, so in order to understand this, we're going to talk about how you virtualize, okay? So the first thing is you have to understand what does it mean to have a virtual machine. So the way a computer normally works is you have the hardware, you have a native operating system that runs on that, and everything runs on top of that, right? Applications, operating systems, stuff on that. But what you really want to do here for a virtual machine is you want to run it in such a way that you think you're running on the hardware, but you're actually running as an environment over that. Again, separating the software from that. And the reason you want to do that is because you want to run multiple different operating systems. I know friends of mine that have Apple computers, they run Windows on it. They make it look like it's a Windows computer. They have that on that. So it started way back in the 1960s. But the whole point is it's efficient use of the real hardware resources by abstracting it from it the way you want it. That's a virtual machine. And you have something called a hypervisor, which is hypervisor is like a supervisor, but it's managing the life cycle of your virtual images, because you can create this image of a machine and then you can take it down again because it's not real. It's all virtualized, right? That's what a virtual machine is. You're riding on top of the hardware, but you're separated from it. So you, like I said, you might think you're controlling a printer, you're actually not. You're talking to a software device, which is actually doing, multiple people could be sharing. In the old days, we used to call something similar in concept a time sharing system, where instead of having one person use the computer, you have multiple people and you have time slice. This is the same type of thing, but as virtualized. There are two types. There's native or bare metal, and there's hosted. In the case of a native or bare metal one, the hypervisor sits on top of the hardware and all the OS images right on top of that. In the case of the type 2 or hosted, they actually have hosted OSs, multiple ones on there being run, and then a hypervisor on top. It's like an extra tiered layer on it. So it's another level of abstraction. Basically, if you've ever heard of VMware workstations or VirtualBox, they're a type of type 2. Most of the other stuff, like the servers like Citrix, Zen servers, and things like VMware, KVM, all those are type 1s. So if you have VMware virtualization, you have the physical machine, you then have the VMware vSphere on top of that, and then you have all these virtual appliances, virtual modules that think they're running on the actual hardware, but they're not, they're running on that. And then you get a whole suite of software you can manage from that and control, and this is a very powerful way of abstracting. That's one way, that's a virtual machine. That's how a lot of the original media processing stuff that was run on software was done 4 or 5 years ago. Didn't work that well. The power wasn't there. Processing power wasn't there. It was too complicated to run. You weren't gaining anything over the physical machine. So something changed. And that change was an open source cloud operating system to make it easy to put things in the cloud. It's called OpenStack. It's basically for infrastructure as a service. It's a way of pooling all your resources, but done as an open source. You don't have to go with any other company on that. And it's done through what's called a representational state transfer, or RESTful API. It was done as an open project. It's managed by an independent association, and it's licensed. So basically, it's a way for you to virtualize your machine without it being tied to a particular vendor, but it opens up a whole bunch of new opportunities. And the best one, and this is the biggest change, is something known as a container. So if you look at the virtual machine OpenStack, virtual machines are bare metal hosts. Doesn't matter which way you do it. OpenStack sits on top of that. And then you have all these virtual machines that are running inside containers, which I'll tell you about in a second. But it's a way of abstracting out for flexibility. And then you're launching an individual image in each one. So it's not tied down to a particular virtual machine. You're now going to virtualize your applications as well. So this is where you tie it into the networking side. Remember, I kept talking about network function virtualization. This ties it in. So you have network function virtualization and virtualized network functions. Doesn't really matter which way you look at it. The point is, you have hardware services at the lower level. You have a virtualization layer, and then you have all these things that you think you're running on the hardware, but you're not. It allows you to really reuse this features for better things. So one key thing I want to tell you about here, saying something is in the cloud is not equivalent to saying it's been virtualized, because virtualized could be a virtual machine, which is not virtual machines. Virtualized is software, but it's not in the cloud. So virtualization simply means software appearing to be hardware. You think you're running on hardware, but you're actually running on another software environment. The appliance code that you have gets shared amongst it. And it's an infrastructure management tool. Cloud computing is about scale and speed. It's about self-service automation, doing things as a service, resource sharing. Doesn't talk anything about the infrastructure environment at all. Who knows how you're virtualizing it? Doesn't matter. Point is, it's a model where you're switching to apps now instead of it's not about virtualizing the machine, what your hardware running, it's what application you're running and how you're using those resources. So if you're going to look at this, traditional IT management, all the services and assets are tied together. It's hard to change it. It's one management team. That's how your IT department works. Cloud management, everything's abstracted. It's not even on your location. You don't even know where it is. You're running something. It's that dematerialized facility. You have no idea where it is. They're just loosely bound. So you have to be able to keep up with what you're working on. Here's where you tie some things together. So the cloud computing service models are as follows. If it's all yours, it's the same as what you're doing today. That's the lowest level. That's the blue on the left. Everything's managed by you. From the networking, storage, hardware, virtualization, all of the application, you own it. And then you walk it across. You have something called infrastructure as a service, platform as a service, and software as a service. The opposite of owning it and running appliances on one end to having everything be leased or not know where it is software as a service. That means you're just running an application. How many people here run Office 360? That's software as a service. You pay a license fee. It's not, you don't own any of that. Microsoft runs it. Okay. Some of the bigger companies will manage local service for image-wise and speed. And then in the other cases, you're running your own applications and controlling your own databases, but your servers you don't own. That's infrastructure. And platform is, you just have the applications you're running. So there are applications running. So they're all different areas of that. Then you might have heard of private cloud versus public cloud. They're really the same thing. The difference is the private cloud, you control it yourself. It's for you. It's still in the cloud. It's still this model of as a service, but it's only for you. It's a single organization. Public cloud runs and looks the same, but obviously since in the public, you have to worry about things like security, right? You don't want someone else accessing your private stuff. And communication, how it works and what your communication to be. And of course, you make up those things. Well, if there's public and private, there must be a hybrid. So hybrid is in the in-between. And the other thing to think about with this, there's nothing stopping you from having on-prem stuff with this as well, on-premises stuff with this as well. Now, here's where the real power of doing the cloud is. And this is this new concept known as microservices. So this is a concept, but it's how you can implement in the cloud. You can't do this in a virtual machine. Remember, you're virtualizing stuff on top of that. This is what's way different. This is how all our new software at MediaKind works. This is a very important distinction here. Microservices is a design philosophy. You break the application into a series of smaller, separately deployable units. Now, these deployable units are all software. So if you take an encoding function, for instance, there's pre-processing, there's filtering, there's the actual encode, there's the packaging to put the thing in and it goes out right. All those can be separate microservices, each one of them. The point behind this is if you define the module and has all its own resources, you can stick it out in the cloud somewhere, and you can then do rapid turn on if you use the device for, as a service. It's very flexible, and remember, it's software, so it runs on whatever available resources out there. So you've completely moved from a physical device that you own that you might have only had on for an hour a day, like an encoder, a contribution encoder, to now it's software running out there. It can be an encoder, a receiver, a transcoder, a packager, a level translator, whatever it is, it's out there. So it's more options for solution scalability, implementations. You can contain failures, operational resilience, because you move from site to site. If the site fails, services are components, a deployable unit, or it could be an API as well, or it could be both. And just to compare what we're talking about, think of it in terms of, if you don't do microservices, we're gonna call it monolithic, right? So you deploy and run an application as one big unit, that's the left. So you have the deployment package, you have all these different things, that's how it's run. That's how most virtualized software is today. It's software, it's virtualized, but it's deployed as a unit. You know, I just mentioned one, Office. Office is a unit, right? What we're talking about microservices is you can deploy each one of these things separately. Each one of those packages. So they all run separately and independently. So each one is its own self-contained, you know, basically virtual machine operating system, everything else, but it's a little microservice that's in there. So the principle is low coupling between the services. It's all API based. It's make it the container, which we'll talk about in a second. Containers is where you carry the microservices. You want to be able to have distributed configuration. So it's redundant and elastic by design because it's this little module. If that one fails, that machine fails, you run it somewhere else. Another module, doesn't matter. You can have infinite instantiations of these services. And then you communicate between the units through the same way regular, we talked about computing resources. You need memory to store results. You communicate through disk and storage. You put a result somewhere and the other thing grabs it. That's how you do it, right? You load balance stuff between the services because you can tell what the load is. You can have analytics being done that says which servers are busy. Don't run on that one. Run on a different server. It's completely, every function is separate and independent, so it scales the best. Very flexible. I know I'm going fast, sorry. You can add services and drop microservices without it impacting the running of the rest of the system because each one of them runs separately. Think of it if you write a recursive subroutine. You get as many recursions as you want, you're not going to affect it because it's a different instantiation. The only thing is, obviously, if you overload a machine by doing too many tasks, then it will slow down. But that's another, make sure you don't do that. So it's all about componentization, loosely coupled, scalable, one service, one domain, and it's designed from for failure from the beginning. So if we take a look at virtual machines, on the left side picture here, you have the server itself, you have if it's a type 1 here, advisor, and then you have all these other guest OS, you have the real OS and then you have the guest operating system, and all the tasks, those monolithic tasks that are running on it. In the case of a container, you now are bundling the library. You now are bundling the libraries. So instead of an OS, there's no OS here. You're only launching this. You said you don't need a whole OS, virtualized OS. You only need the services and functions and libraries you need. You bundle that with the microservice. It's like sticking a little puzzle piece in. Just run what you need. It's very small, very agile piece itself. Instead of in one big application, each one of these. So whatever service it needs, if it's calling something, it will self-contain it. Okay. It's very lightweight. And it shares the kernels and libraries, but it's all isolated. The big thing is isolated contained. But you want to be able to run it at scale, which is a challenge because you got to be able to manage these things, and you need security. Right? You want to isolate these things. So a container is an operating system level mechanism for virtualization, but it's no operating system there. It's like I said, middle level services. Think of it as a container. Basically, you got a big barge on the ocean. You load containers on it. All the containers look the same. So the machine that's putting the container on the ship can be the same arm, right? What's inside that container can be completely different. You don't know what you're transporting on that boat, but the ship is going and the arm of the container is on. That's why it's called a container. So one type of a container platform that manages containers is known as Docker. It's probably the most common one that's out there, but I want to make sure you understand it. Docker is not a container per se. They invented it. Docker is a form that leverages off of using containers. It's just very common. It's available on all the operating systems. And it's all about commoditizing containers, like that container ship I told you about, making everything look the same, and then you can present it in such a way that then another thing that needs it, who's managing your connections, we talked about connection management, could then set up what type of functions you want where. When you do the setup of that is known as choreography, planning it out, and the operation of it actually running is known as orchestration. So an orchestrator would then manage the next level above Docker. So it's all about packaging and layering and keeping everything looking that way. So if we talk about container orchestration, you basically have these containers that contain microservices. If you're going to use that service, you're going to schedule that. You're going to run it on a cluster. The cluster is a way of running services to accomplish a task. Okay. So you assign resources for that. Remember, this is what the orchestrator can figure out. How much resources do I need? Where do I put it? How do I do the load balance for that? And then the orchestration will work with Docker or the container thing in order to be able to do that. And when I say manage the life cycle, it's like you set up the container for that. You have a service that runs in it. You can. It's the software. So you can just say I'm no longer using that service. So you don't have the token for it anymore, and you get rid of it. So it's longer than the as a service, the container, but it's not a fixed item. You can get rid of it anytime you want. That's what managing the lifecycle about. So it's always about really being able to get something to be agnostic, fastly done, and built. You know, think of an orchestrator as a conductor in the front saying how you're going to build your process, all these fancy terms. So the four most common orchestration tools are Kubernetes, which originally came from Google. It was called Borg. And you have Apache, Mesos. Docker itself has one that's now becoming popular, known as Swarm, to compete against Kubernetes, obviously. And they have platform as a service. You do these other two companies here. So Kubernetes, clever name because it's Greek for helmsman or pilot, because it's the one controlling everything together. And it's an open source system for automating deployment, scaling of these orchestrations. So again, you have the tools, you have the host OS or virtual machine, you have the container OS, container runtime, the containers themselves, that would be Docker. Then you have the networking and cluster management stuff, that would be all Kubernetes on top of that. All open source. So the old way, I don't know why, it looks like the slide has an error, and I'll fix this before I make the PDF. I must have got crazy with cut and paste. So ignore the extra stuff that's on there. The old way is you'd have applications running on a host together. It's very heavyweight, large, launching the whole thing. It's not portable. It depends on the OS itself. You can't write it across OS. The new way is a very small function. You get the application itself and the libraries it needs to run with it, but no OS on that. And you use those minimum services. So it's small and fast and portable, and it's completely virtualized from the OS. So whatever runs on that, doesn't matter whether it's Linux, iOS, or Windows. So how do we tie all this together? Well, this is MediaKind's cloud native architecture here. All these things tie together. At the bottom layer, it's either bare metal, running in your own private cloud, using the OpenStack, or you can run a Google Cloud, Microsoft Azure, or AWS. Doesn't matter. That's the advantage of all this. All that stuff is underneath. The containers right on top of that, container runtime, and the pods of microservices, that's the Docker, along with our own code that we wrote as well. So microservices, container, and networking. But the orchestration of that is through Kubernetes services. And then, of course, you have an application management, which is our own stuff on top of it. And then you can do higher level management, which now you can do, since it's all running in a common environment, you can now do analytics, find out, am I overloading, am I not overloading, who's using what services, and feed that back into the system. Analytics and monitoring for that as well. So this is all open standard tools. This is the key. You write the code to make it work, but you're leveraging off of, just like you leverage off of COTS hardware, now you're leveraging off of, I'm making this up, COTS software. You're leveraging off open software interfaces for that. I know I'm rushing through this because we're late. Last thought though, just because I said COTS is a virtualized environment so it can run in the cloud, doesn't mean it can perform fast enough. What we're seeing a lot now is it's still a COTS server. It's still, regular PCI Express buses inside the server, but a lot of people are putting hardware accelerators in now. We do it ourselves. The RX1 I told you earlier, our UHD receiver that got 2110 approved, that has a hardware accelerated card, so we can do 4K decoding in real time, faster. You don't need it to run, it's the same software. It's just that the latency will be, 30 seconds or 20 seconds to decode 4K UHD HEVC. Without it, you put the card in there, it's 300 milliseconds. See the advantage of that? Oh, but then it's not a COT server. It's still a server, still plugs in the environment. It just means that resource is sitting there. So it can't virtualize that move, but in that platform you can get it. It allows you to do it. And by the way, this is no different. We got quick sync, Intel has quick sync video now built in with CPUs. You can have CPUs with attached graphic processing units, GPUs for that. They are FPGAs, or FPGAs accelerated, all these different things you can do out there. So you combine a CPU with specific hardware acceleration, but you preserve the key. It's still microservices. The microservices themselves will make a call. They know that that card's plugged in because there's a microservice that to the software it looks like, oh, I'm calling this microservice, but the microservice is a call to the hardware because everything's abstracted. That's what's cool about it. So I know I rushed to the last part. I was losing people, but guys are all experts on microservices now. We can change microservices and virtualization and cloud and all the stuff. Great. Okay. My exams are back there. You need to take. No, I'm just kidding. Any questions? I know I went fast on that. I'm sorry.
I think one comment is if you like to see Microsoft work as a
Oh,
have a bit.
do we have the blue green?
Exactly.
Oh, this is a great demo. It shows you how microservices can be used to switch software revs like that seamless to the end user. It's a great example of how microservices work. So I
This is
encourage you to see it.
software installed in Amazon website. So we go to here,
So this is code that we wrote to do software migration from one media service to another, changing versions, but it's running in a public cloud. It's on AWS. So it's our code running on AWS to show you how abstract this has become. So that's your dematerialized facility. You don't know where it is.
No más.
Ahora vamos a están sirviendo aquí las chicas de unos sanguchitos, pueden quedar si quieren. Y una cosa más, les quería comentar, muchas gracias, muy amable, realmente muy buena la presentación, muy didáctica y muy precisa, realmente, muy. Thank you very much. Les quería comentar que nosotros aquí en BVS tenemos una división, que es la división de Dell, para todo lo que sea maquinarias, para poder hacer todo este tipo de cosas. Dell EMC tiene toda una serie de soluciones muy importantes. Tenemos un BDM dedicado exclusivamente a eso, que es cross con todos los vendedores. Así que si llegan a necesitar asesoramiento, no solo del BDM nuestro, sino del específica de Dell, no tienen más que comentarlo ahí. Muchísimas gracias y a comer.
Thank you. Thank you. Hey, yes. And then it's on Monday at 2 I'll be at the Yankee Showcase. Oh, sorry, I had to go so fast. Thank you very much. Thank you. Thank you. I appreciate you sticking through 3 hours of lectures.
We're thinking about what you compare the cloud versus on-premise services. It's important to consider in Latin America the cost of internet, because the throughput that you need to send the content to the cloud and operate there. It's too expensive for us. All Latin America.
The good, right, and the good news is though, is that as that gets less expensive over time, which it will, as the infrastructure gets built up, the code is all being written because it's containerized. It follows their own model. So even if you own everything on-prem, it's the same code. It's not even different code. If you buy it from us as an appliance, you actually still get appliances. It's the same code, just put it in the server. Or you could buy the code and put it on your own server, and we'll give you the list of requirements for it, or you can put it in the cloud. See, it's the same code. The only thing that'll be different is if you do one of our hybrids, where we have the hardware accelerate. Well, we don't use GPAs, we use FPGAs, because we don't use GPAs right now. It is for some apps, but for media processing.
But on premises, we cannot offer additional services.
So if you're on-prem, you can have whatever you want in the service. My point was, regardless of which architecture you pick, you deploy it. Everything is on-prem, it's the same code. Everything is in the cloud. So as you find out that your commercial situation changes, where you don't need, where it's not the most economical for you to bring in your brand, you can do some stuff on-prem, and then start to do all this stuff off. Same code.
Thank you very much.
Yeah, yeah, I know.
Por lo que escuché, se va a en todos lados. No.